Of introduction to supergravity. The lecture will be given by Leonardo Castellani, please.
Thank you. Good morning, everybody. So, the menu of this course will be supergravity, and it will be a very basic introduction. And I will try also to be very explicit in the derivations and the calculations. But I will take advantage of the calculations to motivate some approaches that may in fact reduce the computational work for the construction of locally supersymmetric theories. The idea is the following. First, in this lecture I will begin by the very beginning, almost an historical beginning, but I will not follow exactly the history of the development of supergravity, and I will start with the first supergravity theory that has been constructed in 4 dimensions, that generalizes gravity by coupling it to a spin 3/2 field. And in fact, this Lagrangian will be very simple. It will be just the sum of the Einstein-Hilbert Lagrangian and the Narita-Schwinger Lagrangian. And we will prove explicitly supersymmetry, and this will give us some know-how on how to manipulate these fermionic symmetries and prove them in locally supersymmetric theories. So this will be the first step, and it will be very conventional. We will work in X space, that is in Minkowski space, and we will forego geometric interpretation. Geometric interpretations will come later, and this will be the topic of the second lecture, or maybe even this first lecture. We will try to interpret the supersymmetry transformations as, in a geometrical way, as diffeomorphisms into a bigger space that is augmented by fermionic coordinates. So this will be the idea. So here we will deal with the group geometric interpretation. In fact, we will see that supersymmetry, more than the gauge symmetry, is really diffeomorphism. We will prove that supersymmetry here is a local symmetry, but it is not a gauge symmetry. In fact, this is an example of a theory where the supersymmetry transformation will not close off shells, but they will close only on shell, that is on the equations of motion, which is not something you have in gauge theories. Gauge theories, by definition, close off shell with Lie algebra. So this will be the group geometric interpretation that gives some rationale to the diffeomorphism character of the supersymmetry transformation. And most of this group geometrical interpretation has been developed in Torino in the 80s and produces an algorithm, a constructive algorithm for the building of supergravity theories in any dimensions and for any n, for any number of supersymmetries up to 8. And it will be this constructive algorithm that we will use and enlarge. We will enlarge it to include also the presence of p-forms. Here you will have only a field bind and a gravitino in n equal 1, d equal 4, but you know that when we go higher with dimensions or with supersymmetries, then p-forms appear in the supermultiplets. That is, you need p-forms in order to have a representation of the supersymmetry algebra. And you have to include them. For example, in 11-dimensional supergravity, you have a 3-form besides the gravitino and the graviton. But p-forms, you have also the ambition to interpret them in a geometrical way, and the group geometrical way is an enlargement of this, and we make use of a new tool, which are free differential algebras, which are just a generalization of Cartan-Maurer equations to higher order forms. So it is something familiar that will be generalized. And this will enable us to give a group geometrical interpretation in the sense of free differential algebras, also to d equal 10 and d equal 11 supergravities, and even d equal 5. These will be the cases that we will treat in some detail, okay? Since they are relevant to the low energy limit of string theories, superstring theories in 10 dimensions, and M theory in 11 dimensions. 5-dimensional theory is technically important for the ADS-CFT correspondence, so we will spend some time on the 5-dimensional supergravity. And this, more or less, is the main content of the course. There will be some technical notes that I will insert in this discussion, and some of them will be a quick treatment of superalgebras. Since the groups that we are dealing with will be supergroups, because they will contain fermionic generators, and also some notes on spinors in higher dimensions, which will be relevant for these cases. And finally, once you have theories in higher dimensions, you would like to see what they look like in 4 dimensions from the point of view of a 4-dimensional observer, and this will then necessitate some little discussion on Kaluza-Klein mechanism for the reduction of a higher dimensional theory to a 4-dimensional theory. In particular, we will take as examples compactifications of d equal 11, supergravity to d equal 4. Which are a particular type of dimensional reduction, which yields a lower dimensional theory from a higher dimensional one, which is based on solutions of the higher dimensional theory. Solutions of the higher dimensional theory may exhibit a splitting between 4-dimensional space and 7-dimensional space, and we will look at some examples. It is also called, because of being solutions of the equations, they are also called spontaneous compactifications. And this will be more or less the context. Okay. And there will be also the issue of auxiliary fields that are needed to close the supersymmetry algebra. Because you may be interested also in quantizing the theory after having done the classical treatment. These will all be classical, and then you may wonder what happens if I want to quantize supergravity. In fact, that was one of the initial motivations for supergravity, the cancellation of ultraviolet divergences that does not occur in pure gravity, as you know, because of the dimensionful character of the Newton's constant that the theory is not renormalizable. You may hope that it is finite, but it was proven not to be finite by Sagnotti and collaborators in Caltech and Marcus, who explicitly computed the 3-loop counterterm and found that it was not finite. Right? So, from a perturbative point of view, pure gravity is inconsistent from quantum if you want to quantize it by the standard methods of quantization. And so the hope was that for supergravity, you could have cancellations between fermionic and bosonic degrees of freedom in such a way that you would improve the ultraviolet properties. And in fact, you do improve them, but in 4-dimension n equal 1, you do not improve them enough. And the theory, as far as I know, has never been proven to be convergent. I even think that it has been proven to be divergent. This is not the case for the higher, for the theory, the higher the extended supergravity theory is in the equal form with 8 supercharges, and here the finiteness is an open issue in the sense that computations are being done essentially by a few groups. One of them is led by Hilbert, and there, in fact, up to I think 5 loops, no infinities have been detected yet. And there are many conjectures as to what are the symmetries that ensure this conjectured finiteness of higher n equal 8 supergravity in 4 dimensions. So this is a strong motivation, modern, strong motivation for the study of supergravity theories. It may be that supergravity theories furnish you a quantum gravity without recourse of extended objects like strings or membranes or p-branes. So this I would consider today one of the strongest motivations. Of course, if you are interested in string theory, then supergravity comes out as a low energy effective theory. And so you are interested in supergravity also from that point of view, and from the point of view of ADS-CFT that has a supergravity side, and most calculations in these correspondence, in these dualities, are done using supergravity tools. If I have time, the last subject I would add to these notes are topological theories, actually theories that have a topological origin but are not topological themselves, they are dynamical, and they are called Chern-Simons supergravities, which are different from the standard supergravities in that supersymmetry is part of a genuine Lie algebra. Their supersymmetry does not have interpretation anymore as a diffeomorphism in a superspace, but indeed is part of a superalgebra, and the theory becomes a gauge theory, a genuine gauge theory. In X space, gauge theory that closes off shell, no need of auxiliary fields, everything is there. And these kind of theories, even if they differ from Einstein supergravities, well, supergravities that enlarge and generalize the Einstein-Hilbert Lagrangian, they differ. Still, they have equations of motion. You can study them. You can find black hole solutions and so on. And they may be interesting in their own right to study from a quantum point of view. Okay, this is more or less the overview of what I want to do. I'll give some references for the lecture of today. The references, besides the historical, well, the historical in the sense that they were the first to construct this theory in 4 dimensions, and these are Ferrara, Friedman, and Van Nieuwenhuysen. And these are Angelino. This is physics rev D, and it is 1976. D13. And then you have, they are more or less contemporary, Laser and Lima. And it is a physics lecture. Still 1976. The geometrical approach is contained quite exhaustively in a book by Gauria, Frey, and myself, 1991. World Scientific. the standard space approach, standard component approach, I would call it, to supergravity, you find in the physics report by Peter van Nieuwenhuizen. The physics report by Peter van Nieuwenhuizen is, I don't have it here, but it is, I guess, 1981. The title is Supergravity. Okay. I should mention also a reference that marks the birth of supergravity as a low energy theory of strings, or superstrings, and it is the Liozzi, Shirk, and Olive paper that recognizes supergravity as a low energy limit of the 10-dimensional superstring, and it is called Supergravity and the Dual Spinor Model, and it is in Physics Letters 65B of 1976. As you see, this year was quite important for the development of supergravity theories. Okay, of course, the motivations are not complete. In the list of motivations, I should also give you the standard motivation one gives for local supersymmetry. You start from rigid supersymmetry that you may need for the hierarchy problem or cosmological constant problems and so on. And then you argue that you need to consider this symmetry as a local symmetry, and this brings you to supergravity. Supergravity then may enter the standard model and produce some solutions to some old problems in that model. But I started from another kind of motivations that I find even most compelling. Okay, so this being done, dealt with, we can start from the beginning in the development of the four-dimensional theory. Are there questions so far? Well, historical questions at this stage. So the first chapter of this lecture will be the Rarita-Schwinger field. Well, that goes back to the axiom that was wrote down by Rarita and Schwinger many years ago, and the Lagrangian in flat space is simply a generalization of the Dirac Lagrangian. But now you have, in the game, you have a spinor that has also a word index. And instead of having a slash, you have this structure sandwiched between these two gravitinos. The gravitino field is a spinor that has a spinor index that here is not appearing explicitly, and the word space a curved index that I will call mu. This object, as you see, has a spin content that goes up to 3/2, because this counts for spin 1 and this for spin 1/2. And when you add spins, you have a 3/2 part of this object that has a spin. You have a spin 3/2 part, but you have also a spin 1/2 part that you may eliminate by an appropriate gauge choice, and this gauge choice, in fact, that we eliminate will be gamma mu sin alpha equals 0. This will select for you if the gravitino obeys this condition, then this will select the pure spin-free half part. But let's start from here, and you recognize here that you have a gauge invariance. We are in flat space. You find a gauge invariance that is very simple. If you vary the gravitino by the derivative of a spin 1/2 parameter, then you see here that you will have invariance, but I have to tell you something more. The something more is that you need also to impose a kind of reality condition on the gravitino to match degrees of freedom between bosonic field that I will have later in gravity and this Fermi field. And this reality condition is called Majorana condition. And it will be the following. It will relate psi bar to psi so that they will not be any more independent fields, and you should not vary them independently then in the variational principle. And indeed, it will be such that psi bar, which is defined as usual with gamma 0, is equal to something that relates it to psi, that is psi transposed times the charge conjugation matrix in 4 dimensions. This is the Majorana condition that I will use, in fact, to have something that resembles a real quantity instead of a complex quantity. It reduces the degrees of freedom by factor 1/2 of the general Dirac spinor in 4 dimensions. Okay, these are the rules of the game. And then you see here that if you insert this here, you need to vary only one of these fields. If you vary psi sigma because of you find that this, because of the antisymmetrization of rho and sigma, this is in fact invariant. This is in fact invariant. That is, you should vary here and you should vary here. But the variation here and the variation here are in fact equal, because for Majorana fields, you have for Majorana spinors, in general, you have this equality. If I take 2 Majorana spinors, lambda and chi, you have, and this is a quick exercise, gamma 5, gamma mu chi is equal, you can reverse the order, chi bar, gamma 5, gamma mu, lambda. This is very easy. You just write down the bars in this way, and you do some gamma algebra, which maybe I should mention just to have the conventions of the gamma algebra in 4 dimensions that I will use. So, in order to prove these equalities bilinear in spinors, in Majorana spinors, I need some conventions, and I will write them here. Essentially, you need these. Now, the metric that I will use, this is not important in the present discussion, but I will fix conventions to be this. Then the Clifford algebra between gamma matrices will be normalized as follows. Then the anti-commutator of two gammas will be written as a matrix gamma with two indices, anti-symmetrized. Then the gamma 5 is defined as I times gamma 0, gamma 1, gamma 2, gamma 3. My epsilon symbol will be such that epsilon 0, 1, 2, 3 is equal to 1 and is equal to minus epsilon 0, 1, 2, 3. And then what other? Then for the moment, that's it. And then I have to tell you what are the properties of the charge conjugation matrix. And all the properties originate from this definition. The charge conjugation matrix on any gamma give me minus the gamma transposed. So the charge conjugation matrix serves the purpose of finding the transpose of the gamma matrices. So from this set of rules, you are, actually from the last one, you are able to prove explicitly, which I did as a small exercise. This is a one-line proof using this. And the fact that I didn't tell you that C is anti-symmetric for dimensions.
Is that the case for one-form spinors or simple?
No, this is the case for spin 1/2 spinors. For one-form spinors, there would be a minus sign. It's true. These are spinors that are zero forms. Yes, in fact, let's add these rules here. We collect them here because we can have some use for that. If you take two zero forms, you find these rules. In fact, you find that only the identity, the gamma 5, well, here you have a minus sign. I can take all the list of the Dirac bases of the 16 gamma matrices. You find minus sign for the gamma mu and the gamma mu nu, and all plus signs for the others. This is what I already wrote, plus reverse. And finally, you have the gamma 5, which is with a plus sign. These are all the preliminary exercises one does when you start doing computations in supergravity in 4 dimensions. This is it. Now, if you have spinor one forms, in fact, I have not introduced yet the language of forms, but we will do it. We will do it in the following, in the sense that psi mu, that I will consider gravitino psi being, by definition, psi mu dx mu. Then, if you have one forms, because of the anti-commutation of the differentials, these rules are subject to a flip of sign, so that for one forms, we have minus, plus, plus, minus, minus. Okay. If you have never done this computation, just try to do the first 2 or the first 3, and you understand why it works this way. Now, then you will understand that if you vary this, you put the variation here, and because of this rule, you can flip it, and it gives you 2 times the same contribution. So in fact, you need to vary only this one. The variation is just the variation you obtain by varying this and putting a factor of 2. So if you vary this, it's clearly invariant, and so you see that there is a local gauge invariance that is given by this rho. So the Rarita-Schwinger field here under this transformation leaves this Rarita-Schwinger action invariant. Now, we have subjected also this field to a gauge condition, and this is a gauge condition in the sense that it breaks the gauge invariance. It breaks this gauge invariance, but by breaking the gauge invariance, it selects also the spin 1 3/2 part of the field. Now, the field equation is, well, you have to vary this. Again, the variation, you can vary, for example, only this field, because the variation on psi bar and psi add together, and so you find as field equation, if you vary this Lagrangian, you find mu rho sigma, gamma phi, gamma nu, d rho psi sigma is equal to 0. This is the field equation of the Rarita-Schwinger field. Now you can multiply this equation by gamma mu. You multiply this equation by gamma mu, and you see that here you reconstruct the gamma mu that are anti-symmetrized. So you reconstruct something like epsilon mu rho sigma, and you have well, you have gamma phi, gamma mu, and then d rho psi sigma. But now, this quantity here, we should maybe add it to the list. Gamma mu multiplied by gamma phi, in fact, gives you the dual of gamma rho sigma, and with the factors, the correct factors of my normalization, this is exactly given by here, given by this gamma phi, gamma mu, therefore AB is equal to I half epsilon AB gamma CD. So this is gamma matrix equality in my normalizations, and then you see you can use it here, and you find that this is simply gamma rho sigma d rho psi sigma equal to. This is a consequence of the equations of motion. But this you can also write. This is gamma rho sigma, gamma B is also equal to gamma A, gamma B minus eta B from these rules. And so this you can also write as gamma rho, gamma sigma, d rho psi sigma, minus d rho psi rho. And then you see what this implies. I just rewrote this consequence of the Rarita-Schwinger field equation. I rewrote it in these ways by splitting this gamma rho sigma into a sum. Now, why did I do this? Because now you see this gamma sigma goes inside because this is a constant matrix. We are in flat space. It's a constant matrix. It goes inside, and it is contracted with the psi sigma, but we know that the contraction with the psi sigma gives 0. So this is 0 by the gauge choice. And so you see that the equations of motion imply also transversality on the spin 3/2 field. They imply this equation here. So the field equations together with the gauge choice imply transversality on the spin 3/2. Finally, the last observation on the free Rarita-Schwinger Lagrange I will mention before coupling it to gravity is the following to prove that it is a massless field. And this you see immediately by taking this equation here and multiplying it by gamma mu. This is still a consequence of the equations of motion. Now, there is a formula that gives you the multiplication of a 1 index gamma with a 2 index gamma, and I will write it maybe here as part of this gamma technology, and you have the gamma mu. Gamma, well, let's call it gamma mu. Now, I'm making no distinction between curved and flat indices because we are in flat space, and so it's the same thing, but they will be, of course, distinguished when we couple gravity. And I will say how. This gamma mu, gamma rho sigma, you can rewrite as a gamma mu rho sigma, that is the product totally anti-symmetrized of 3 gamma matrices. Plus, and here I need some space, delta, well, plus delta, it is actually an eta, mu rho, gamma sigma, minus delta mu sigma gamma rho, because it has to be anti-symmetric in rho and sigma, because this was anti-symmetric in rho and sigma. So these are standard formulas for the multiplication of multi-index gammas between themselves. And if you use this, then you find that this reduces to gamma mu rho sigma, 0 psi sigma, plus you have this piece that gives you plus delta mu rho, delta mu rho in fact. And I have a gamma, and I have a gamma sigma here. But you see, this gamma sigma will kill this psi sigma inside again, and so that this will be 0.
What has plus sign?
Sorry? I rewrite it better. Plus eta mu rho gamma sigma 0 psi sigma. Okay, but this gamma sigma psi sigma again 0 minus you have a delta mu sigma, it's gamma rho.
This is eta.
0 psi sigma. Yes? Right? This eta, it is an eta, yes, you're right. Sometimes I write delta, sometimes I write eta, but it is always eta. So don't worry. So this really tells you that here that there is a psi mu. But you find here the Dirac equation. In fact, this first piece is nothing but the equations of motion. This first piece is nothing but proportional to the equation of motion. I wrote them in this way, but this is really proportional the gamma mu rho sigma. This gamma here, it is another identity, is proportional to the gamma with 3 antisymmetric indices. You see, you have the mu rho sigma that are free, well, actually here, no. Yes, mu rho sigma indices that are free. No, this is contracted here. But mu rho sigma, mu sigma. Okay. Gamma mu rho sigma is proportional to this. And if one wants to be precise, I can give you also the proportionality constant. I write it here. Gamma AB. See? 3 antisymmetrized indices is minus I epsilon A B C D gamma phi gamma D. So here we are building our gamma technology dipole. All these identities you can prove very easily. The easiest way to prove them, well, of course you can start from the basic algebra, but the easiest way to prove them is to specialize it to particular indices. You choose 0, 1, 2 or 1, 2, 3, and you find these equalities. Then you recognize that this field equation you can rewrite as this gamma mu rho sigma on the rho psi sigma, which means that this is proportional to the field equations. This is proportional to the gauge condition, and so you are left with this that has to be equal to 0. It's a consequence of the field equations. But if this has to be equal to 0, you see that this gives you this ledge on psi mu 0. And here you find the Dirac equation for this spinor. But you know that if this ledge on psi mu is 0, this also means by applying another this ledge that this is box psi mu is 0. And this shows you that psi mu is a mass equal 0 field. That's it. That will be the last bit of this analysis in flat space for the Rarita-Schindler. Now, we will erase everything except the Rarita-Schindler Lagrangian, because we will couple it to the Einstein-Hilbert action. Is it clear so far? Yes?
Just to confirm that the constraint is a gauge choice rather than a constraint put in by hand.
I'm sorry?
The constraint is a gauge choice, gauge
yeah.
fixing, rather than the constraint put in by hand.
Yes, yes. Yes, because I want the field to have a pure spin 3/2 content. And I see it as a gauge choice. Okay, now I think I did not leave out any detail so far. Now we couple it to gravity. So the coupling to gravity follows the usual rules. Instead of the partial derivative, you write down the covariant derivative with a spin connection that I call omega. My conventions for the covariant derivative are the following. The covariant derivative of any spinor, lambda, are equal to the usual derivative of the spinor lambda minus 1/4 gamma mu. Well, let's put first the spin connection, omega AB mu. Well, mu gamma AB lambda. So my conventions are a factor minus 1/4. And the gamma mu here is curved index for the gamma. Now I have to distinguish them from flat indices, and they will be distinguished in this way. This is the gamma A with flat index, which are part of the algebra. These are numerical matrices. When they have these flat indices A, B, we call them flat indices. And gamma A is a numerical matrix. While now the mu indices will be curved space-time indices. And the relation will be via the Hilbert field, as usual. It will be the relation. So gamma mu with a curved index is an x-dependent matrix, in fact, because here you have the field, which is the Hilbert of the manifold, that now we are considering to be also possibly a curved manifold, not anymore flat Minkowski space. So these are the two ingredients I have to add in order to couple it to gravity. This is the standard procedure you do to couple a spinor field to gravity, or in fact any field to gravity. But for spinor fields, you really need the Hilbert formulation. Okay, then you have this coupling, and this will give you the action. And the action will be the following. The action of supergravity then is the Rarita-Schrödinger action and the Einstein-Hilbert action. The Einstein-Hilbert action I will write in this. Now I'm using forms, in the language of forms. But I will convince you that this language of forms that I'm using is exactly equivalent to the usual, leads exactly to the usual Einstein-Hilbert-Lagrangian. These I write in this way. Now I'm writing symbols and then I'll explain them. This will be what is known as the Einstein action, and then you will have the Rarita-Schrödinger action. In fact, there is a minus sign. Here I put an A, which will be a constant that we will determine, and in fact is not so important because it defines the normalization of the gravitino, gamma A. This is it. Now I will explain the symbols that you probably know already. And the symbols are defined as follows. Okay, the first symbol is this RAB. RAB is really, by definition, a two-form. This way, this is a two-form, is called the curvature two-form. VA is the Hilbert one form, is really dx mu. This is the Hilbert one form, this is one form. And RAB, VC, VT multiplied by epsilon ABCD, you can readily recognize as the Einstein Lagrangian, which I will do quickly. It is rather easy to do, actually. I can do it here.
Are we missing
yes?
psi in the action, the redistributive action on the bottom line?
There is a psi. There is a psi here. You're right. You're right. yes, I should also tell you that psi, then, as we saw before, is psi mu dx mu, is the Gravitino one form. Right? And you recognize here you have a 2 plus 1 plus 1, you have a 4 form here and a 4 form here, because the exterior d is the exterior derivative on this one form. Exterior derivative. Now, I'm assuming that some basic differential geometry is known, so I don't know, I will not so far, I will not now define exterior derivative and so on. But okay, I just reminded. The exterior derivative on a P form is defined to act in, is defined in this way. If you take the P form, a P form, you can expand on a basis, on a coordinate basis, as follows. It will have components, and it will have antisymmetric components. Mu1 up to mu p dx mu1 exterior product dx mu p. Okay? This is one way of expressing the P form, expand it into a differential basis. These are exterior products of these differentials, so this whole thing is antisymmetric in mu1 with P, and then this means that this thing here is antisymmetric in mu1 in P. So forms, or differential forms, are just a compact way to describe antisymmetric tensors. Since antisymmetric tensors appear in supergravity theories, in higher dimension supergravity theories, you understand that the form language is essential to reduce the number of indices that are floating around. Not only this, the language of form is also essential in any theory that you want to be geometrical. Because this theory, written with these diffeomorphism invariant operations that are exterior product and exterior derivative, is by construction invariant under general coordinate transformations. So I'm using forms because of these two reasons. The first one being that it is the natural language to write down a geometrical theory invariant under general coordinate transformations. The second reason is, in fact, that the P forms are really the quickest way to encode properties of antisymmetric tensors. But here I did not finish by definition. Well, the definition of this is easy. This is simply defined as derivative on mu0 of p mu1 mu p times here dx mu0 dx mu1 dx mu p. This is the definition of the exterior derivative. As you see, the exterior derivative brings a P form to a P plus 1 forms, because here you have P plus 1 indices. And this thing has P plus 1 indices, and in fact, all these indices are really anti-symmetrized because this product of differentials in the coordinate basis anti-symmetrize this set of indices. So if you wish, the exterior derivative of a P form is really in components, is nothing else than the curve of the antisymmetric tensor. Okay, that was just a quick reminder of what I understand by exterior derivative. Then this is not an exterior derivative, but it is a covariant exterior derivative. And so here, I will just give the definition of the covariant exterior derivative that will simply mimic the covariant derivative in components that I gave here, and the covariant derivative of psi then is defined by the usual derivative of psi minus 1/4 omega AB gamma AB psi. Okay, will be exactly the same definition, and as you see here, this is a two form, because this is a one form and this is an exterior derivative, and this is also a two form because here I wrote omega AB, but omega AB is again, I should add it here to this list, it is omega AB mu, which is the usual spin connection, gamma AB, dx mu. Is also a one form that you should add to this list of fields that are that enter into this Lagrange. So I think everything has been defined. Here I have exterior products which build up the so-called exterior algebra of differential forms. But for simplicity, I don't want to put this wedge symbol everywhere. So for simplicity, from now on, I will erase this symbol that I should have put also here, because this is a one form, this is a two form. But I don't put it anymore, and it is understood that when you see two forms multiplied by each other, they are always multiplied by an exterior product. Exterior product is this thing. Are there some things unclear? Forms are well known, more or less. Just not to begin again by linear applications on tangent vectors and so on. I just need them for granted.
Sorry.
Yes?
On your definition of difference,
Yes.
you never use normalizations like 1/3 factorials.
No, I'm not using it. I'm not using it, and in fact, I define the component of the forms with a normalization of 1. Yeah, this is a point that can give some numerical trouble if you don't follow the same conventions. But my normalization will always have strength 1. Yes. Okay, now this is a proposal, of course. Now we have to see whether this proposal is consistent, and in fact, we will have to prove that this is a supergravity action that has an extra symmetry besides the usual diffeomorphic invariance, general coordinate invariance, and Lorentz rotation symmetry. You see, all these contractions are done with Lorentz invariant tensor. This is the Lorentz invariant tensor, the epsilon symbol with flat indices in 4 dimensions. Epsilon A, B, C, D is a Lorentz invariant tensor in the sense that if you apply Lorentz rotation to this, since Lorentz is an SO13, then the determinant, this is a conserved tensor, since the determinant of a Lorentz transformation is equal to 1. And here all these contractions are done with the epsilon AB, which is the Lorentz invariant metric. And then this whole thing is invariant under Lorentz rotations, local Lorentz rotations. And it is invariant under general coordinate transformations. Now there is a third invariance in this action that will be supersymmetry, and that we will discuss in detail. So from now on, we deal with forms and not anymore with components of forms. Just to anticipate what will be the geometrical interpretation, I will mention that all the symmetries of this action will be in fact related to a supergroup, and the supergroup will be the super Poincaré group. Here I will give you just an aesthetical reason of why it will be so, because you can see what are the fundamental fields in these Lagrangian. The fundamental fields are the Vielbein, as one form, are the spin connection that I'm keeping now independent of the Vielbein, and so I will work in the so-called first order formalism, and are the Gravitino field, one form. All these fields will be in correspondence to generators of a group, and the supergroup will be the supergroup associated to translations, Lorentz rotations, and supersymmetry transformations. And they will close on a Lie algebra, which is actually a Lie superalgebra, that is called the super Poincaré Lie algebra, where you have a subgroup relative to the bosonic generators that are closing on the Poincaré algebra, the usual Poincaré algebra, and then you add these fermionic charges that will have non-trivial commutators with M, a trivial commutator of Q with P, and a non-trivial anti-commutator of Q with himself. And this will be the super Poincaré algebra, Lie algebra, that will be at the geometrical basis of the invariances of this Lagrangian. So this, I anticipate the role of these fields as in some way dual to these generators. But now we are forgetting this. We are just proceeding without any group theoretical insight. We are just proceeding to check what are the invariances of this Lagrangian. Okay, in particular, before checking supersymmetry, I said that we were into first order formalism. Omega is kept distinct from, well, independent of V. Now, here I will examine some field equations you deduce from this Lagrangian. The first field equation that I want to examine is the one that you obtain in the variational principle by varying the spin connection. Now, from the definition, actually, here I forgot to define the quantity, which was this RAB. I did not tell you how this RAB in fact depends only on omega, and I forgot to give you the definition of this RAB, which I should have given you, and the definition is this one. RAB is defined to be the exterior derivative of the spin connection minus omega AC omega dB, and here you have eta in eta C D. Okay? This is the definition of this field. It's two-form, the curvature two-form. Now I hope everything has been defined. Okay. Okay, then I perform the variation of the spin connection in this action, and what do I get? Now, you remember that when you vary the curvature that depends on omega in this way, this is quite similar to what happens when you vary Yang-Mills field strength in the field. It gives you, in fact, the covariant derivative of the variation of the connection, in this case the spin connection. So this is just the covariant derivative of the variation of the connection, d omega EB. Covariant derivative of the variation of the connection. Very easy. d r b is equal to d omega EB minus d omega dc omega dB. Well, CD minus omega EC d omega dB eta CD. And this is what I define as covariant derivative. This is by definition the covariant derivative. As you see, because it is the covariant derivative of this, because the covariant derivative, if you write it in components, acts first on this index and then on this index with the spin connection. And here it comes. Spin connection acts CD on this index here and on this index here, CD. So it is the usual rule, if you translate it into components, is the usual rule of covariant derivative of an antisymmetric contravariant tensor. Okay, if you use this rule, then you find what is the variation here. You find that the variation of the Lagrangian is, now, you have d delta omega b, which is the variation here, dc dd, epsilon dcd, plus, then you have to vary the omega, which is here, and here it is only here, and then you have a minus a over 4 psi bar gamma phi gamma b gamma b psi vd. Is it correct? Yes, because the omega was here. The covariant derivative d was defined as correctly d minus I minus 1/4 omega AB gamma EB. Right? It acts in this way on a spinor, so if you vary here, you are left with a 1/4 gamma AB. 1/4 gamma AB.
Should be plus sign in that case?
It should be plus sign.
Well, depends where you put the delta omega.
Yes, you're right. You're right. It is not a plus sign because here the delta omega would be here, but the delta omega is a one form, and if this one form you put it at the beginning, as I will do, then it jumps over this one form and gets an extra minus sign. So it stays minus. It stays minus. But here also, I will have to factor the delta omega. Well, let's put it here, delta omega. Minus delta omega. So this is the variation. Now here, to have a free delta omega, I have to integrate by parts this exterior, covariant exterior derivative. And if I integrate by parts, then, this I can do because I'm considering really the variation of action, and I'm taking boundary values that go to 0 at infinity. So, if I integrate this, I can integrate by parts. And when I integrate by parts, I don't have an extra minus sign because this d acts really on a one form. So what you get by integrating by parts is the following. It's d omega dt, and then you have this d, well, this is covariant d on v, c, then you have vd, epsilon EBCD. Then you should act on this one with a minus sign, but this really only doubles the contribution because these two things commute. And then you are left with this minus delta omega AB, and you have this thing out. So you have all these things here. Now I can factorize the delta omega AB to impose that the variation of the action is 0, and you find the field equations to be given by 2 times covariant derivative on the field line times another field line by epsilon minus a over 4 psi bar gamma phi gamma d gamma ab psi dd. And that's it. This is the field equation that you obtain by varying the spin connection. Actually, from that field equation, we will be able to express omega, thanks to this field equation, to express omega in terms of field binds, of derivative of field binds, and inverse field binds and bilinear M size. This you can see from the structure of the equation. We do it in detail, but you can see it already in the structure of the equation because this is an algebraic equation for omega. As you see, omega appears only algebraically. It does not appear as a differentiated quantity, but it appears algebraically because here it is inside this d that there will be an omega, and here there is an and here you just have psi bar psi. So we will be able here, from this equation, to extract omega as a function of dvv and psi bar psi. This will give us omega as omega that depends on v and on psi. So this equation is the equation that will reduce the theory to second-order formalism, in which the only independent quantities are the field bind and the gravity.
Sorry,
yes?
What happens to the second term from the integration by parts? First form equation. So you've integrated the first term by parts to get the 2 delta over AB.
Yes.
Minus something which looks like the first.
Yes.
But so how does that combine with the factor of A over 4 there, right?
Sorry.
So yeah. So here you're
from here to here.
Parts, yeah.
From here to here.
No, that's okay because I understand you get
yes
2 delta omega and then you get minus delta omega AB times the thing above it. Is that what you were saying?
Yes, I'm saying that I'm integrating by parts, so really I should take this off and put it here, but on both of them.
Yeah, sure.
On both of them, it means that this is the first one, and the second one, you would have to transfer this here.
It's actually so I understand how you get the first term, but then this minus delta omega AB, what happens to that there?
Oh, it's here, minus A4. I'm just taking this out. Is it okay?
Yeah,
So
sorry.
factorize, well, I'm considering dl over delta omega AB. Then I take this out.
Okay, thanks.
I just integrated by parts to have it free in front of everything, and so this gives me the infinitesimal variation due to the variation on omega, and then I'm just factorizing the way the variation of omega, since it is an arbitrary variation, right? As usual in the variational principle, I take arbitrary variations and then I can factorize them since they are arbitrary.
Sorry.
Yes?
So what's the role of gamma phi? Is that just a convention or some character consideration?
No, it is there and also in the Rarita-Schwinger-Lagrangian, if you remember, because of parity reasons. If you want this term to have the same parity, to behave under parity in the same way as the Einstein term, you need this gamma 5. Actually, you can understand it in components. You have a gamma 5 times an epsilon. And both the epsilon and the gamma 5 transform with a -1 under parity, so that the combination gamma 5 and epsilon transform with +1. Okay. So we got these equations of motion that I will rewrite here for future reference. dvc, dv, epsilon, dcd, minus a over 4, we said, minus a over 4 psi bar gamma. And then we have gamma ab psi. Correct? Yes, psi b. This is the so-called torsion equation, because we will interpret this as a torsion later on, and this torsion equation gives me omega in terms of dm. Now, I want to convince you of something. If you never saw the Einstein-Lagrangian written like this, I want to convince you that this is indeed the Einstein-Lagrangian. It's not difficult to see that this brings you exactly to the Gauss tensor, the scalar curvature, times square root of minus g times dx4. Let's do it. We do it once for all, and then the same thing you can do for the equations of motion and so on. But I'll do it here on the action. So what you have to write down is RAB, BCVD. This is a 4 form. Now this 4 form, this 2 form, I can expand on a field-bind basis. You could expand it on a differential basis, coordinate basis. But this can also be expanded. You can choose your basis on the cotangent space, and I choose here to expand it on the field binds, because the field binds are also furnishing you a cotangent basis on the M4 manifold you are playing on. So this is the expansion on another basis, and it is the so-called flat basis, because you see it is labeled by flat indices. And here you have flat indices everywhere. Here you would have indeed this exterior product, but I'm not putting exterior products in. Okay, if you expand it like this, then you recognize here the Einstein-Lagrangian that I wrote here to be the following: RABCD. Well, actually, I call them EF, VE, VF, and this is this first thing. And then I have BCVD, and then I have epsilon in BCD. And here I recognize explicitly the 4 form, but I also know that, let's put the correct normalization so that everything will come out to be exactly like the Einstein term. Yes. Equal. Here I have R, A, B, F. Now I'm expanding this, all these B's, I expand them on a coordinate basis. These are 1 forms, and I write them as dE mu dx mu, g mu f dx mu, and so on. Because ultimately I want to make contact with the usual Einstein-Lagrangian, so now I'm expanding these on this basis. and an epsilon. Okay? Then this is equal. Now, this is equal to R A B E F. You have still this V F mu V 0 V sigma epsilon BCD. But now, this thing here, you can rewrite, this is the volume element in the sense that it is equal to epsilon mu rho sigma, since this is 4 form, it is the top form, is equal to the epsilon symbol with mu rho sigma times the volume element, which is dx4. This recognizes the volume element that you rewrite in this way here. You recognize it because this is being anti-symmetrized mu rho sigma, the only 4 form that exists is dx1, dx2, dx3, dx4, well, dx0, dx1, dx2, dx3, and this is the d4x. And if you change the order, then this epsilon mu rho sigma takes care of the change of order that you are doing in multiplying these exterior differentials. So this is it. But now you see that these indices mu rho sigma of this epsilon, which are curved indices because they come from this volume element in curved coordinates, then they get transformed into flat indices because they are contracted with this Hilbert field. So E mu E contracted with this transforms this index into a flat index. And so this thing times this thing converts everything in the following equation: R A B E F, and you have epsilon E F C D, epsilon A B C D, and then you have a determinant of V D for X. Well, yeah, what I did, in fact, is even easier. I took this epsilon symbol and combined it with this, but this is the definition of the determinant of this matrix times the epsilon EFCD. This is by definition the determinant of the matrix. You contract it with this, and this gives you by definition this matrix here. This times this. Because this times this. Definition of determinant. But now I'm finished because you see here I have the determinant of this Hilbert matrix. And here I have two epsilon symbols. These two epsilon symbols are contracted. They are contracted on two indices. And here there is a nice formula that tells you that the contraction of epsilon symbols is equal to 2 factorial times 2 factorial, which means 4. And then you have an anti-symmetrized delta EFAB. This is the rule where anti-symmetrized delta is defined in this way. The anti-symmetrized delta is defined in this way: 1/2 delta AC delta BD minus delta BC delta AB. And in general, you can have anti-symmetrized deltas with n indices. and they are defined into 1 over n factorial, and then you have all the permutations with signs of these things. Here you have the sign of the permutation, and you have all the deltas. So it is the sum over all the permutations of the deltas with a sign according to the permutation. It is the anti-symmetrization of products of deltas. Since you have n factorial terms, you divide by n factorial to have strength 1. It is quite general, and quite generally also, the contraction of 2 epsilon symbols in any dimension are given by the following: epsilon A1, AP, B, C1, Cn, well, CQ, contracted with epsilon B1, BP, C1, CQ. So I'm taking 2 epsilon symbols in any dimension, in P plus Q dimensions, and I'm contracting Q of them this way. This gives you always the result. It gives you a delta anti-symmetrized with indices, free indices A1, BP, B1, BP, and then there are some factors, combinatorial factors. There's a P factorial, a Q factorial, because you are really summing over all the permutation. And then you have still one thing that has to do with the signature of the metric you are using to lower and raise indices. And it is, in fact, the determinant of this metric here, of determinant of eta. In this case, the determinant is -1. It would be -1 anyhow, even with the reverse signs. So here, there is a minus due to the determinant of eta. There is a 4 because P is equal to 2 and Q is equal to 2. Okay, and now you see I'm finished because this anti-symmetrized delta simply identifies the EF indices with the AB indices, and this comes out to be equal. This whole thing comes out to be equal -4 R AB AB determinant of V, but determinant of V is just square root of -G, and then you have D4x. And this is nothing else but the scalar curvature, and then this is the invariant volume element in a curved space. So you see that you can write explicitly in this way, in the form language, the Einstein term, the Einstein Lagrange.
Sorry.
Yes?
It's the epsilon mu nu rho sigma Levy beta. You just erased the epsilon mu nu rho sigma, the Levy beta
Yes.
tensor density or symbol.
It is the Levi-Civita tensor in any dimension, yes.
So there is a.
Sorry?
So it's not numerical 1 or -1. You mean?
Now, the epsilon ABCD is the numerical 1 and -1. The epsilon mu nu rho sigma, no. It is not the numerical 1 because it is really a mu a, well, it is the V's that multiply the ABCD. But here, yes, I had a mu rho sigma, but this I contracted with this in order to give determinant of this matrix. And the determinant must be multiplied by this to take into account the anti-symmetry of this matrix. Okay, this contraction with epsilon symbols we will use quite often in these calculations, so it was good to mention it. And so I have proved to you that this is indeed the Einstein Lagrangian. Analogously, and actually much quicker, you can prove that this is indeed the Rarita-Schwinger Lagrangian. You just put curved indices here, 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 and here, and then if you have the dx, 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 and this really produces you an epsilon, that is the epsilon that was multiplying the Rarita-Schwinger Lagrangian components. So this is immediately recognizable as the old Rarita-Schwinger Lagrangian, but where you have introduced the covariant derivative and you have introduced, you see this VA that is contracted with this gamma A in order to produce you the gamma B. Okay. But we have this equation. We have this equation. Now, this equation I want to solve. I want to solve. And I will solve this equation now, once for all, and then we will see that we pass the second order formulas. Okay. Okay, let's first solve the equation in the absence of psi. And then to add the psi will be very easy. If psi is 0, we have to solve this equation here 2 times exterior derivative of the field bind covariant dd epsilon abcd equals 0. This is a 3 form. Now, for short, let me give a name to this exterior derivative of the field bind. I will call it the torsion, and it is a 2 form, and then it will be defined as this. Exterior derivative of field bind, by definition, is derivative of the field bind minus omega A C V D epsilon C. This, in my convention, is the exterior derivative of the field bind. This is how it acts, right? Because now it acts on a vector index, and it acts on vector index contraction with the spin connection. Okay? So this is my definition, and this is what I'm calling now for short the torsion. Actually, it is the usual definition of torsion in Riemannian geometry. I call it RA. I use the same symbol of the curvature, but with only one flat index. There is a reason for this, because we will see that I will interpret it as the curvature of if you wish, the field strength of the field bind, exactly as the Riemann curvature you can see as the field strength of the connection of the spin connection. But I'm calling it RA. So I have the equation RC VD equal epsilon ABCD equals 0. Now I'm asking, what is the solution of this equation, which was the first one we considered by varying omega? Okay, I'm telling you what is the answer, and then I will prove it. This really implies that RC as a two form, because RC is a two form, is 0. This implies that RC as a two form is 0. It is not evident from the equation, of course, because there are indices contracted and so on. So it is not immediate that this implies this, but we have to prove it. Okay? Now we prove it. Okay. Then we rewrite this equation, expanding RC into the Filbine basis, and this is done simply by calling EF VEF, and this is RC. And then we have VD epsilon ABCD, and the whole thing has to be 0. Fine. So this is really, this I want to keep. Okay, this is. So this is really R, C, E, F. Then I have VE, VF, VD. And then I just add a fourth Filbine that I call VG, epsilon ABCD, equal to 0. This is a Filbine. Of course, if this is true, also this is true. So I'm just exploring the consequences of this equation. The consequence is this. But now you see, I'm playing the game on this top form to write it as an epsilon symbol times the determinant of V. So this is C, E, F. And then I have epsilon ABCD. And then this VE, this thing here, this thing here, this thing here, can be rewritten as an epsilon F, EF, DG. The order was EF, DG. And then I have a determinant of V and a V for X. Here. This is an epsilon F, DG, determinant of V and V for X. This is the way that the top form in the Filbine language is translated into the top form into the coordinate language. You have this determinant and you have this. It is the same reasoning that we did before, and I can reduce it to this. How do you do it? You expand it in coordinate bases. You recognize that this is a determinant. The coordinate basis is this, and the determinant is multiplied by this. But now you recognize again the contraction of two epsilons, where only one index is contracted now. Only the D index. These are free, these are free. And then I can use the same trick as before, the contraction of two epsilons. And here you would have a 3 factorial times 1 factorial, and then you have a delta EFG anti-symmetrized ABC. ABC, EFG.
Doesn't matter the order of the contraction. I mean, it doesn't.
Yes, in fact it does, but you see that I took care of this because I brought this D here to have it at the last, and I have a minus sign. But then the minus sign combines with the minus of the metric and gives a plus. So this is equal to 3 factorial, and then you have R, and then you have RCEF. And you have this thing, DE, A, DF. But actually here I will put a FD, and here a new delta DG C. These are all anti-symmetrized. I rewrote these, I can rewrite in this way because this EF, anyhow, anti-symmetrized. It's very easy to see that this is it. So this is equal, and now I'm splitting the sums, and this is equal to R, C, D, because you see EF converts this anti-symmetrized delta, converts these indices AB, but I still have a delta here, which is a delta GC, plus, but then here I have three terms, because I have to cycle over ABC in order to recover the whole anti-symmetric combinations that I have here, and cycling it over ABC, I put the C here, then I have A here, and the B here, and you find RC, we said BC here, delta GA, plus RC, CA, delta GB. Here you can consider three terms. 1, 2, and 3. ABC, BCA, CAB. Okay, I cycled over the three terms. Okay, and this is RCAB. That the C becomes a G, GAB, plus RCBC, delta GA, yes, plus RCCA. Okay, that was useless. Okay. Now I can contract the two indices G and A. G and A, G and A. Contracting these two indices gives me finally, if I contract G with A, it gives me R, A, B, plus 4 times, because the contraction of G with A is the delta, gives me a factor 4, R, C, B, C, plus R, C, C, B. Contract is this G with A, but here there is a B, so this is B. And all of this, remind, has to be equal to 0. But then you see here you have the same object that is summed, and the sum is not 0 because it gives you 1. It gives you 1 minus 4 because you have to convert this, plus 1. 1 plus 1 minus 4, it gives you minus 2R A B equals 0. So you have that this object has to be 0. R A B has to be 0. But now, if R A B has to be 0, it means that this is 0 and this is 0. The whole thing has to be 0. But then also this has to be 0. And you recognize RCAB has to be 0. And we proved what we wanted to prove, that the torsion equation, this equal to 0, implies RABC equal to 0. So we proved that varying the spin connection into our supergravity Lagrangian brings in an equation whose first part we have solved. We have solved the equation when this is not here, without this. So far we have considered only the bosonic part. Okay, we just proceed slowly to solve it, to to solve the equation now. RA equals 0, I told you at the beginning, that enabled me to express the spin connection in terms of the field line. Now I'm taking really psi equals 0. Then we will add psi, but this will be done in one shot. It will be very, very quick. Is it clear so far? And now this is a rather standard procedure. It is a rather standard procedure that I will record once for all, and then I will apply it also to the case with non-vanishing psi. So I found that dVA minus omega AC V d epsilon CD equals 0. I wrote it as a two-form. This as a two-form, we said, is equal to 0. RA is equal to 0. It is an output of the equation of motion for spin connection. And now I want to solve this equation for the spin connection. Okay, so the trick is the following. We expand this equation on a coordinate basis. So on dx nu, dx nu. This is a two-form. So on a coordinate basis, it will become the curve of VA minus omega A. Well, I will write it like this. Mu mu. Now, and this is contracted with this. Look, I'm just writing dV like this, and this means really a contraction with the epsilon, with the eta metric. It is a shorthand for this. Just not to write every times eta. Okay, now this equation here has to be equal to 0. I wrote in components the content of torsion equals 0. Now, the strategy is this. I multiply this equation by eta AC dc rho. And then I sum cyclic permutation in mu mu rho with signs plus plus minus. I sum everything, and out comes the answer for omega. So let's do it here. With a bit of patience, epsilon AC mu A 0 C minus omega B mu B mu B rho C. Okay, epsilon AC 0 C, epsilon AC 0 C. This is the first term. I have two other terms like this, which I obtain by cyclic permutation of mu nu rho, and I take here a plus sign, d mu rho. You probably already saw these in gravity courses, but I'm just redoing it once, because it will be repeated in the case of fermions. I will not have to repeat it in the case of fermions. Rho and mu are the first indices here. And this is it. And everything has to be equal to 0. Actually, now what I will do is to write down explicitly these anti-symmetrization. So I will write it like this. I take out the square brackets and I write down explicitly what they are. They are the anti-symmetrization, which in my conventions has always strength 1. So here I have minus 1/2 and a plus 1/2. Omega of mu nu mu nu. Here there was mu rho, here there is rho nu. And it will be mu, see, and here same thing, rho mu, now here there is mu rho. Okay. And now I cancel the terms. You see that this term cancels with this term is equal, but with a sign difference. Yes, sign difference. Because here there is a minus, and here we have this minus, but you see that the two are interchanged, and so actually, wait. Oh yes, yes, there is also the eta that has to take care. This eta, in fact, identifies these two indices, and here the eta AC, I'm just putting the eta AC inside to identify indices. Everywhere I see a C, I put an A. Everywhere I see a C, I put an A. Okay, in this way. And now I can identify. Now I can subtract this with this, and this goes away with this. Okay, and that's it. And you are left. And with the sum of this, you are left with omega mu AB d mu d rho A equal to minus d mu d A mu d A rho, and you have the three terms. See, you have this that survives, this survives, and I put it here, and then I write the three terms dv, because this sums with this sum, so the factor 1/2 becomes a factor 1, and then you have 1, 2, 3 terms that I'm writing here on the right hand side. And d d rho with d A plus d rho d mu A A. Okay. And this leads you to the final answer for omega nu with indices A, B. These are lower with the metric equal to V rho A D mu B. Now I'm just multiplying by the inverse field line, to free this. I'm multiplying here by the inverse field line, and this is the inverse field line minus d mu. And this will be the formula, the final formula that gives me what I was telling from the beginning. Plus, and that's it. That's it. This is the formula that gives me the spin connection in terms of the field-bound field and the inverse field-bound field and its derivatives. It's a bit tedious, but this is the trick one always uses to go from the torsion equation equal to 0 to the second order formalism that allows me to express the spin connection in terms of the field bind. Yes, implicit expression of E in terms of field, of omega in terms of field. Is it all correct? There may be some mistakes. I hope not. But this is the general philosophy. You can check it. You can check all the indices. Okay. Fine. Now I'm telling you what we will do in the next lecture. In the next lecture, we will add fermions. We will define a super torsion that will have also a part into a bilinear of psi, since the equation for the torsion will have also a part bilinear in psi. And then we will define the torsion as this minus something that will be psi gamma a psi. And then everything will be repeated. Here, instead of having only dVV, we will have also psi psi, but nothing will change in the structure of the equations. And so the solution will be exactly the same. This solution will be this plus a bilinear term in psi. But this we will not redo it in detail. We will just use this to give the explicit solution. Then, once we have done this, which is the transition from first order to second order formalism, then we will explore supersymmetry, and then we will reinterpret everything as a group geometric theory on the super Poincaré manifold. Okay, there are questions?
So the solution that the torsion equals 0 is basically assuming that the field line is non-zero.
The what?
The field line is non-zero.
Yes. Yes. The field bind is assumed to be non-degenerate. Yeah, because the field bind really is a transition from the coordinate bases in curved bases, with the dx mu's, to a local tetrad, right? And this transition, I always assume it is one-to-one. I mean, it is non-degenerate. There are always at every point of the space-time 4 independent tangent vectors. If you assume this, then the field bind is non-degenerate, and its metric and its determinant is different from 0 and so on. Then you're right. One could consider more interesting situations where you have some degeneracies and some collapse of dimensions, but it is not this case. Okay.